probably the last lecture that we have. It's not really a lecture. In this video, we are going to revisit some of the concepts that will help you prepare for your final exam through question and answers. So, we have prepared a few questions for you, and we have also prepared, of course, the answers. What we will do is we will go over these questions, and hopefully this bunch of questions that we have prepared covers some of the most salient concepts. But I should also add a disclaimer here that these questions in no way necessarily resemble what you should expect to see on the final exam. And I hope by now that you have had a somewhat wonderful and of course sometimes a bit tiring journey. The subject, as you must have realized by now, is not a basic one. It's a somewhat advanced course, but quite useful in many signal processing areas. And yeah, so I sincerely hope that you have had a lot to benefit by sitting through the video lectures and solving the assignments. So, let us start our journey, and what we will do is here in this question we will look at the concept of cross correlation. So, we have two signals here, x1 which is sinusoidal, and x2 it is a cosine signal, and there is a phase shift to this cosine, and the question asks us to compute the cross correlation between these two signals. In fact, strictly speaking, it should have been cross correlation function, because we are specifying lag. If you do not specify the lag, it is pure, it is understood to be a static cross correlation, and all one has to do is go back to some of the early lectures where we talked about cross correlation. Maybe if you want to answer this question, you want to have that slide handy where the definition of cross correlation function is given between two signals, and you can see that these two signals here they are not your finite energy signals, they are periodic signals. So, you should use the appropriate definition of cross correlation, and it is always a good idea to have an intuitive feel for the answer before you sit down to compute the exact answer. So, what do you think should be the answer intuitively? On one hand we have a signal that is sine, and then on the other hand we have a signal that is cosine, but phase shifted, right. Now, if you go back to trigonometry, some basic trigonometric identities, one of the identities says that cosine theta plus pi by 2 is minus sine theta, right. So, in other words, the second signal, although it is a phase shifted cosine, because it is phase shifted by pi by 2, it is nothing else but negative 2 sine 2 pi k. In other words, you have x1 which is a sine 2 pi k and x2 which is minus 2 sine 2 pi k. As a result, if you look at the correlation between them, and because correlation is a normalized measure, the answer turns out to be minus 1, right. The negative sign comes about because of the negative sign on the signal x2. Of course, the second signal has an amplitude of 2 as well, but correlation does not look at amplitude differences. As long as they are identical in a normalized sense, you obtain minus 1. So, let us move on to the second question. So, as you can see, now we are moving from cross correlation to the next concept in this question, which is concerned with sampling. Fairly simple question, but kind of tests your understanding of sampling and aliasing and recovery of the continuous time signal from its sampled version. So, the question says that we have a continuous time signal of frequency 50 hertz, and it is being sampled at 40 hertz, and the resulting signal is denoted by xk. The question is asking us what is the frequency of the continuous time signal that would have been ideally reconstructed from this sampled signal. So, the procedure to solve this is to first determine xk. We are given that x of t is has a frequency of 50 hertz. You can imagine it to be a sine wave of frequency 50 hertz, and it is being sampled at 40 hertz. All one has to do is go back again to your sampling lectures, sampling basics, and write the expression for xk. Let me write that for you on the board. So, I have x of t, let us say of some amplitude a, frequency 50 hertz, and now this is being sampled at 40 hertz. We know from our sampling basics that the resulting discrete time signal is also a sine of frequency f small f, where small f is given by f over f of fs, and f in our question is 50 hertz. So, I have 50 over 40, and that gives us 1.25, right. Therefore, the discrete time signal that I have is a sine 2 pi 1.25 k. And if you recall from the discussions from the lectures that we had on aliasing, this sinusoid of frequency 1.25 cycles per sample manifests as a sine 2 pi 0.25 k due to the periodicity of the discrete time sinusoid. In other words, what has happened, again this is a repeat of what we have learnt in aliasing. What has happened is I should have seen a discrete time sine wave of frequency 1.25 cycles per sample, but I end up viewing it as a discrete time sine wave of frequency 0.25 cycles per sample, and that is again because of the trigonometric properties of or the properties of this trigonometric function. Now, for all practical and theoretical purposes, therefore, the signal that results as by virtue of sampling the continuous time signal at this sampling frequency is a sine 2 pi 0.25 k. And when I try to recover, let us say I have this ideal Shannon reconstructor, when I try to recover the continuous time signal from this discrete time signal, it fetches me again a sine wave whose frequency, let us call that as 2 pi f hat, let us call this as x hat, the reconstructed signal, whose frequency f hat is given again by our familiar formula f times fs, and f is 0.25 and this is again consequence of sampling. A fast signal has been undersampled. What should have been the minimum sampling frequency as per the sampling theorem? It should have been 100 hertz, but unfortunately we have sampled it at 40 hertz, and therefore, this fast signal manifests as a slow signal, and in this case it turns out to be 10 hertz. So, that is the answer that we are looking at. All right. So, this is just a simple calculation for you, but the more detailed calculation was on the board. So, let us move on to the third signal. We are given a signal again a sine wave, and this is a finite duration sine wave, unlike the sine waves that we are generally used to, which exist forever. And we are being asked to compute the magnitude of the fifth coefficient in the DFT of the signal. So, if you again browse through your lecture notes, you will see that expressions for DFT have been given. All one has to do is bring up that expression for DFT and compute the resulting expression. It is a bit just drudgery kind of work here, but that is okay. We will have to be prepared for all kinds of questions. So, the DFT expression is given to you on this slide. and we are being asked for the fifth coefficient, but remember the counting in the DFT coefficient sequence begins from n equals 0. Therefore, the fifth coefficient is obtained by plugging in the value of n equal to 4, and one has to just go through this summation by plugging in the value of x of k. An easy way out perhaps is to rewrite x of k in terms of your Euler's expression and then bring it in here and use some of the nice properties of the summations of complex exponentials. That would make things easy for you, or if you have a calculator and you know how to use a calculator, you can actually plug in those values and get the correct answer to be as 8. Okay. So, let us move on to the fourth question. Now, if you read the fourth question, the situation is reverse to that of the third one, where we are given the DFT sequence of a signal, and here we have 6 coefficients. Assuming that this is an n point DFT, we must realize that the signal also is of length 6, and what we are being asked is the value of the signal at k equals 3, which means the fourth coefficient in the signal sequence. So, obviously, the procedure here is to use the inverse DFT expression, and do not forget the 1 over n in the inverse DFT expression, which is what you see in the formula that we have reproduced here for you, and all one has to do is plug in the values of the DFT coefficients into this expression and again go through the calculation. Remember, we are interested in the value of signal at k equals 3. So, substitute the value of k accordingly and you should obtain the answer to be minus 0.65. All right. So, that kind of covers the concepts associated with correlation, sampling, DFT, and now we come to the theoretical part where we are looking at the Fourier transform of an infinitely long signal. Again, this question allows us to refresh our concepts on the theoretical Fourier transform. X of omega is given to us. This is understood to be DTFT, and there is another signal which is y of k. As you can see, y of k is x of k minus 4 in the numerator by 2 in the denominator. So, what this means is y is essentially a scaled and shifted signal version of x, and what we are being asked is the magnitude of y of omega at a specific frequency omega equals pi by 2. Of course, if you have a lot of time and you do not know what to do with that time, you could actually now adopt a long approach, time consuming approach, which is to first construct x of k by taking the inverse Fourier transform of x of omega, and then you can construct y of k followed by a discrete time Fourier transform of y of omega, and then taking its magnitude at omega equals pi by 2. That will hopefully consume all the time that you have, but you do not want to do that. Rather, you want to use the properties of DTFT that we know, and there are two operations being performed on x. One is scaling and other is shifting in time. We know throughout the course by now we must be used to scaling so much that you should know the property of this Fourier transform by heart, which is scaling in time. What does it do to its Fourier transform? So, you have, for example, in this question you have y of k as x of k by 2 minus 2, although we are being given k minus 4 by 2, you can rewrite as x of k by 2 minus 2. Let us take x of k over 2 alone. X of k over 2 is a scaled version of x and the scaling factor is 2. We know that any signal when it is scaled by a factor of a or s, x of k over s, its Fourier transform changes to x of s omega. So, which means now the first operation, which is scaling by a factor of 2, alters x of omega by 2 omega, that is in place of omega you replace 2 omega. So, you have you evaluate now x of 2 omega, and x of 2 omega would be 4 omega by pi cos square 2 omega, followed by a shift in time, and we know shift in time results in a multiplication by e to the j omega d if it is shifted by a value of d, and the value of d here is 2. So, the final answer for y of omega would be 4 omega by pi cos square 2 omega times e to the minus j 2 omega. But the shift, the modulation, let me say that the multiplication of e to the j d omega or minus j d omega does not make a difference when you are computing the magnitude. Therefore, it turns out that this shift has no impact on the answer at all, right, whereas the scaling does have an impact, and that is it. So, you would have 4 omega by pi cos square 2 omega, and we are supposed to evaluate y of omega at omega equals pi by 2. You plug in the values and you should get the correct answer to be 2. Let us move on now to the concepts of energy, where we are being asked, we are being given a continuous time signal. As you can see, it is an exponentially in fact amplitude modulated sine square signal, and the signal exists only at non-negative times. The question is asking us to compute the energy of the signal. So, if you recall, the energy of the signal is given by integral mod of x of t square dt. On the face of it, the integral may look very intimidating, because it would involve essentially integration of 4 e to the minus 12 t sine to the power 4 2t. Now, that is a fairly intimidating integral, as these integrals can be quite painful. So, to simplify matters, it may be a good idea to rewrite sine of 2t in terms of again Euler exponentials. So, you rewrite sine 2t as e to the j 2t minus e to the minus j 2t by 2j, and then you have nice integrals that you can work with. Even as you square, things do not become quite complicated as much as they do otherwise. So, you work out the integral patiently, and you should get an answer of 0.05. That is the energy of the signal. It may be a good idea for you to check this answer in MATLAB, although you will not have access to MATLAB in the regular written exam, but just to cross check whether you are correct or not. How will you check whether this answer is correct in through the use of MATLAB or any other numerical software? Well, essentially simulate x of t over a very fine grid time t and then sum up the squared values. Essentially what you are going to do is you are going to replace this integral with a summation, and dt would be your sampling interval, right. So, if you do not forget to multiply with the sampling interval, then you would get a blown up answer as you increase the number of grid points in time. Now, we are slowly moving into the concepts associated truly with time frequency analysis. So, this question is asking us to calculate the instantaneous frequency of a signal at some time t equals 1.5. The signal is given to us. If you recall, so it is time to actually browse through and read through the slides and the notes associated with instantaneous frequency concepts. And if you recall, the definition of instantaneous frequency first requires you to construct an analytic representation of the given signal, a of t times e to the j phi of t, and the instantaneous frequency is given by the derivative of the instantaneous phase. So, all one has to do is take this signal and rewrite it in analytic form. When you do that, in fact, the nice thing about the signal is that you should be able to rewrite this in analytic form fairly easily. You do not have to compute any Hilbert transforms and don't get into all of that. By visual inspection, write the analytic form so as to get A of t as e to the root t minus t square and phi of t as 2t square plus t, so that the instantaneous frequency is simply the derivative of phi of t, which is 4t plus 1, and at t equals 1.5, obviously the instantaneous frequency is 7 radians per second. So, that is pretty straightforward, but allows you to revisit the concepts of instantaneous frequency and analytic representations. Now, moving on to the next question, there is a big jump here. Whoever has designed the question paper decided that you should take a big leap and from instantaneous frequency to the concept of frames. What we are given here is that E1 and E2 constitute an orthonormal basis for the two-dimensional Hilbert space, and 3 vectors are constructed from this E1 and E2. If you look at the concepts associated with this question, first you have the concept of a basis, which is nice. You can go back to one of the earliest lectures where we defined what is meant by basis. Then there is a concept of orthonormality. So, if you recall, basis, any set of vectors constitute a basis if they are linearly independent, and orthonormality requires that their inner products are 0, that is number 1, and the magnitude of the 2 norm, you can say the 2 norm of the individual vectors should be 1. So, that is what is required of orthonormality, for orthonormality, and therefore, E1, E2 here you are given that E1 and E2 are orthonormal. As a result, the inner product between E1 and E2 is 0, and both E1 and E2 have unity 2 norms. So, now we have 3 vectors, you can say, or 3 functions, basis functions, gamma 1, gamma 2, gamma 3, constructed from this 2-dimensional space. Obviously, you should expect gamma 1 and gamma 2 and gamma 3 not to be constituting a basis, because E1 and E2 are already basis. You cannot construct a higher dimensional basis for a higher dimensional space using only the basis for a lower dimensional space. So, the question that is being asked is, given that gamma 1 and gamma 2 and gamma 3 are constructed in this particular fashion from E1 and E2, what and you are given additionally that gamma 1, gamma 2, gamma 3 constitute tight frame. In fact, maybe you just want to check in the course of answering this question, you may end up checking that as well. So, now what you have to do is, again you have to refer to the notes on frames, and remember, frames are a generalization of basis functions, where the set of vectors or functions that one is considering need not satisfy the linear independence property that is required of a basis, and they can be redundant. So, as you know, there can be different types of frames. You have tight frames, you have orthonormal frames, and so on. Here we have a tight frame, and we are supposed to figure out the bounds A and B. For that, one has to recall the classic equation that one encounters in the context of frame theory, and that equation here is given for your reference, A x2 square, that is, when I say x2 square here, square 2 norm being the lower bound and b times the square 2 norm of x being the upper bound for the sum of the projections of x onto gammas. So, what one has to do is essentially invoke this relation, and and then the next step would be to compute the sum square projection coefficients, which is sum of mod of inner product between x and gamma and square, right, and then figure out what are A and B. In order to do that, it is good idea to first express here or recalculate our x. So, in general, for any vector x in the 2-dimensional space, one can write as alpha 1 E1 plus alpha 2 E2. So that the squared 2 norm of x is alpha 1 square plus alpha 2 square, and using the fact that E1 and E2 are orthonormal, and the expressions given for gamma, just some simple calculations will show you that the sum square inner products between x and gammas are earlier I said projections, but the correct term is inner products, because projections are normalized, projection coefficients are normalized inner products. So, the sum square inner product coefficients turn out to be 20 alpha 1 square plus 20 alpha 2 square, which you can write as 20 times alpha 1 square plus alpha 2 square. So, straight away you see the answer to be 20. Very good. So, now the next question takes us further into the world of wavelets, and we are given the Fourier transform of a wavelet as sine square omega times cosine omega. I do not know what kind of wavelet this corresponds to in time, maybe you can figure out. But right now the question has given us the Fourier transform of this wavelet, and it is defined over this interval 0 to pi by 2. So, you should indeed check that this is a wavelet. Remember, one of the qualifying properties of wavelet is that its Fourier transform at 0 frequency should be 0, and indeed it is. Okay, so, we are given this wavelet and we are supposed to calculate the peak frequency. For all practical purposes, some function has been given, and we are as a function of omega, and we are supposed to be determining the peak value. So, use your standard ideas from optimization, find the derivative of this function, the derivative exists, and once you do that and go through simple calculation, simple derivative, remember this is in a product form. So, you have to use a chain rule for calculating the derivative, do that and then solve for omega, which turns out to be 0.96. So, you should get the equation as tan square omega equals 2, which means omega is tan inverse square root of 2, and that turns out to be 0.96 radians per second. As an exercise, you should indeed check that this is the peak, and there are two ways of doing that. One is to calculate the second derivative and look at the sign of the second derivative at this peak frequency that we have calculated, and if it turns out to be negative, then you know it is a maximum, otherwise it is a minimum. The other way is to just plot this function in MATLAB and see if indeed you get 0.96. Okay, very good. So, let us now move on to the 10th question. We are moving further now. We do not know whether we will take a U-turn later on, but we are moving further, where we are being asked to compute the DWT of a sequence. The sequence is given to us. It has a length of 8 observations, and the question is not asking us to compute the DWT. If you read carefully, it is intended to compute the DWT. So, somebody else would compute it, we need not worry. The question is focused on the extension of the signal. So, it is fairly much deeper into DWT. Remember, some of the practical aspects that we discussed for DWT, we had mentioned that we would need to extend the signal, and we had talked about symmetric extensions, periodic extensions and so on. Here we are doing a half point extension, and in a half point extension the symmetry, whether you look at the left or the right, would be such that it would be midway between the border values. So, for example, here in this sequence we have 2.2 as a first value and 3.4 as a second value and so on. And if you were to look at the left extension, why am I interested in left extension? Because the question is asking me to look at the left x at minus 2. If I look at the left extension under the half point extension idea, x at minus 1 would be 2.2 and x at minus 2 would be 3.4. So, the symmetry lies between 2.2 and 2.2, essentially 2.1, and under such an extension we have just answered now the question, value of x at minus 2 is simply 3.4. fairly simple question, but it's a good thing because it forces you to go and re-look at the extensions, different extensions that one has. All right. Then we have the approximation and detailed coefficients in the next question from the 2-level DWT. So, somebody has done the DWT for us, which is very good. It says 2-level DWT, that means I have x at some level, normally we say it's level 0, and then you would have A1 and D1, level 1 decomposition, and A2 and D2 at level 2 decomposition that stems from a decomposition of A1. So, in total we have A2, D2 and D1. It is clear from these coefficients that the length of the signal must be 8. But what we are being asked to compute is the energy of the signal, right. Now, what is of course not given here is what kind of extension that has been used. And we know again from the different extensions that we discussed in the lecture, only the periodic extension preserves the energy. Otherwise, there would be no way you would compute the energy from these coefficients, that is you would be able to compute the energy of the signal. So, you can state that if question is not stating that explicitly, and the only way to calculate the energy of signal is by making that assumption. So, make that assumption. Assuming periodic extension, we know that Parseval's relation is obeyed, which means energy is preserved. As a result, the energy of the signal is the sum square of these coefficients A2, D2 and D1, and that turns out to be essentially 1260. Okay, good number. So, remember that it is a periodic extension that preserves the energy. Now, here is a slightly different question, but maybe focusing on a different property of the DWT. We are given the reconstructed approximation and detail. These are not coefficients, as you can see from the notation. They are the reconstructed versions. A1 and D1 are given to us, but there is one value that is missing in A1, and we are being asked to find that out. So, how would you solve this problem? If you are given the signal, it would be great, because you know that from the perfect reconstruction property, which is satisfied for all extensions, right. So, we do not have to worry about extension. Then I would simply say A1 plus D1 is a signal and find out the missing coefficient. But now I am not even given the signal. So, how do I solve this, right? Well, there is another important property, useful property of these reconstructed components, which is that A1 and D1 are orthogonal to each other, that is the inner product is 0, and when you use that property, you can recover the missing coefficient in A1, and that is minus 0.18. Okay. So, here it is a nice twist to the problem. We do not use Parseval's relation, we use a perfect reconstruction property. Let us look at the 13th question. In this question, the details are given from the coarsest decomposition of a finite length signal, all right. So, what would a coarsest decomposition mean? It means that I have gone to the coarsest possible level. For example, if I am given a signal of length 8, then the coarsest possible level would be 3. So, the first level would give me 4 coefficients, second level 2 and a third level 1. And then when I reconstruct the signals corresponding to those such a decomposition, I have A3, D3, D2, D1, right. Then that is what I would obtain if I had a signal of length 8, and the reconstructed ones will also have the same length as the length of the signal. Using this idea and applying that to this given question, we see that D1 and D2 are of length 4. They are reconstructed components, and we know that the reconstructed components have the same length as the length of the signal, which means the original signal has a length of 4. and we are given that its coarsest possible decomposition. So, what this means is there is a signal of length 4 and it has been decomposed up to level 2. I have A2, D2, D1 as the small ones as the coefficients and the uppercase ones as A2, D2, D1 again. I am given D2, D1. And now, I am also given that the energy of the signal is 3.3532 and I am being asked to compute the mean of the signal. So, what is the relation between the mean of the signal and the coarsest decomposition? How does this value of energy that is given to me useful in answering this question? Well, the foremost thing that one should remember is when one does a coarsest decomposition of a signal in DWT and reconstructs the components, the approximation component that one reconstructs essentially is going to be at every point in time is simply going to be the mean of the signal, because the coarsest approximation of any signal is simply the mean. That is the central idea that one wants to use here. In other words, A2, the big A2 is simply going to be M, where M is the mean of the signal. Good. So, that property we have used, where M is the mean of the signal. What we mean by mean is simple sample mean, the average of the observations. How do you find out the M? That is where you use the energy of the signal information, and basically we can apply the relation which is energy preserving relation, the sum square of the sum square 2 norm of the signal, or square 2 norm of the signal is simply the square 2 norm of big A2 plus square 2 norm of big D2 and square 2 norm of big D1. Remember, there are not going to be any cross terms because A2, D2, D1 are all orthogonal to each other. So, you use that property essentially and find that out. So, the first step is to realize that we are talking about a coarsest approximation, and the coarsest approximation, we are not talking of the coefficients, is simply the average of the signal, right. And what we are given further is energy. So, for example, and we said we use the energy preserving property. For A2, the square 2 norm would be simply 4m square, and for D2, the square 2 norm would be the sum square coefficients, and D1 would be another sum square coefficients. So, 4m square plus sum square 2 norm of D2 plus sum square D norm of D1, 2 norm of D1 would be 3.3532. That would get you M to be minus 0.41, it could be plus 0.412. So, there is that ambiguity, but that benefit of doubt you will always get. So, that is the idea. So, look, and this is a very nice question because it helps you revisit a lot of interesting properties relating to the DWT of a signal. All right. So, as we said and we expected, we take a U-turn here. We have come back, we have gone in full circle, gone up to DWT, reached the peak, and then come back to sampling just to make things lighter. So, here we have a continuous time signal which is given by x of t as sine square 10t times cosine t, and the question that is being asked is what is the minimum sampling frequency that is required to avoid aliasing. Well, that is fairly easy. You express x of t as just sum of sines using the trigonometric identity, find the maximum frequency, and the maximum frequency turns out to be 6.37 hertz, that is in cyclic units. Therefore, the minimum sampling frequency that is required to avoid aliasing is twice the maximum frequency, which is 12.74 hertz. Very good. And now we have the next question, again a jump. So, that was just a break for you. Now, we are back again to the joint time frequency analysis. Here, interestingly, we are given a figure like some of the problems that you must have seen in the assignments. What we are given here is a spectrogram using a Hamming, that has been obtained using a Hamming window of width 48 samples, and the signal is given to us as being some signal corrupted by an impulse. Of course, if you look at the spectrogram, you should be able to guess what else is there in the signal. But what we are definitely given is there is something plus an impulse and plus some noise. And the question that is being asked is, what is the frequency of the signal at time t naught? Now, you must understand that there is no way from the spectrogram straight away one can answer this, because also the question is not so perfectly well posed in the correct sense, because we know from the duration bandwidth principle it is not possible to pinpoint the frequency. So, the way to read this question is around t naught what is the frequency, approximate frequency, and that turns out to be, if you read from the graph, first of all, where do you locate the impulse? You know that an impulse has a uniform spread across all frequencies, and you search for that pattern in the figure, and it is fairly easy to see that it occurs somewhere between 60 and 80, but that is not so much of interest. Somewhere it has occurred, and what is of interest to us is the frequency of the signal. What we mean by signal is the main signal, the underlying signal. Remember, the overall signal is made up of some maybe signal, it looks like a chirp like signal, plus an impulse and plus noise, right. So, we are interested in knowing the frequency of that signal that is being corrupted. So, we walk up along the frequency axis at time t naught where the impulse has occurred and realize that the frequency is approximately 0.3 hertz. Remember, on the y axis the units are hertz, and that is what is being asked. So, be careful with the units, sometimes questions can be a bit tricky. Okay. All right. So, that is it, and then now we move on to the 16th question. What would be a question bank set without Wigner-Willi distribution, right? So, here we have a question relating to the Wigner-Willi distribution. If you read the question carefully, it says the ideal TFR, ideal time frequency representation, is shown in the figure below. And by now you must be familiar with ideal TFRs, even your time frequency toolbox plots that. So, this ideal TFR essentially says what are the time frequencies, what are the frequency distributions in time for the signal that you would ideally obtain. So, here we are given 3 coordinates, right, and then surrounding and then there is a band of frequencies over a short duration as well. So, you can think of it as some kind of a modulation in time, amplitude modulation in time, and also frequency, some kind of frequency modulation. So, there are 3 atoms here, so to speak. We have used this term atoms, and the question that is being asked is, if I were to compute the Wigner-Willi distribution of such a signal, that is, which has these 3 different components, what would be the highest frequency of the interference term? Remember, the plain vanilla Wigner-Willi distribution results in interferences, and the interferences occur exactly midway in the time and frequency plane, and we are looking at here the signal that has 3 components, and you can now count the number of interferences that you would obtain, and we are being asked for the highest frequency of the interference term, and the highest frequency would be midway between this frequency here at the bottom and the frequency at the top. Therefore, the answer is 0.25. It's fairly straightforward, but it's nice. It's a good example. Again, allows us to revisit the concept of Wigner-Willi and the interferences. Okay, so we are back to wavelets. That was a good detour to Wigner-Willi. So, we are given here the high pass filter corresponding to an orthogonal wavelet function. Remember, for any orthogonal, when you have DWT, you have a wavelet filter and you have a scaling function filter, right. Wavelets can be specified in terms of the filter coefficients. Here the wavelet is being described by the filter coefficients, and what has happened is one of the coefficients has gone missing. We do not know where, and we are supposed to find out this missing coefficients. We are given that it is an orthogonal wavelet function. What does it mean? We know from the property of wavelets that the sum of the impulse response coefficients of the wavelet filter should be add up to 0, and therefore, the missing coefficient we have discovered as minus 0.0327. So, very straightforward, but good simple question. The next question that we have is a signal, the discrete time signal. It is an exponential signal over this period 0 to 15. So, it is a finite duration exponentially decaying signal, and the question that is being asked is the approximation of the signal constructed from the coarsest possible decomposition using a Haar wavelet. Now, this is one of the concepts here is something that we have looked at previously. Remember, we talked about the coarsest possible decomposition earlier. The coarsest possible, the approximation constructed at the coarsest possible decomposition is simply the average, right? And it does not matter whether you are using a Haar wavelet or anything here, it does not matter. That is only to probably distract you from the mainstay of the question. What is important to see is that the length of the signal is 16. Therefore, the approximation, we are not talking of approximation coefficients here. The approximation would also have 16 coefficients, and as a result, the answer is simply the average of that exponential signal, finite duration exponential signal repeated 16 times, and that is the answer for you. Now, we have a discrete time signal that is being given to us, and we are supposed to determine the discrete time Fourier transform. So, we are back to Fourier domain. So, some kind of zigzag is happening, which is good, allows us to go back and forth, fairly straightforward. There is nothing much to think here, simply invoke the DTFT and write down the answer, right. So, this question we have not given the complete answer, fairly you just have to work out the exponentials and come up with your answer. Now, this question again has come from your model question paper, where we have asked you to discuss the differences between short time Fourier transform and wavelet transform. So, unlike the previous questions that we have seen, here we have a descriptive kind of question, they are not quantitative questions here. What we are being asked is to discuss the differences, theoretical differences between short time Fourier transform and wavelet transform. Ideally, I would say just go and read the notes we have and listen to the lectures on STFT and wavelet transform. Many a times we have pointed out some key differences, right, but you want to start off sorry, with the most important difference, which is that the short time Fourier transform and wavelet transforms use different types of window functions, right. When we say window, essentially windowing the signal. In fact, you by now you must be an expert in TFA, time frequency analysis, and realize that any joint time frequency analysis requires us to use duration, that is finite duration signals, finite duration analysis functions, and therefore, it is a good idea to start off discussing the differences between STFT and wavelet transform based on that concept. We know that the short time Fourier transforms use finite duration sine waves, that is clipped sinusoids, whereas wavelet transforms, they use finite duration waves. Sometimes they are not exactly finite duration, but most of the energy is contained in a finite duration. Modelet wavelet is one such example, but by and large that is the idea. So, the difference between these two in that respect is the finite duration window, the analyzing function STFT is created by beginning with the sine wave and clipping off its wings. whereas with the wavelet coefficients, we start with a function that is limited in time. We do not take a function and then clip it. And what is the impact of that, that operation, that is the way we choose this, it has got to do with the time frequency tiling, right. The main difference is that the windowing in time and filtering in frequency are tied together very nicely in wavelet transforms, whereas in short time Fourier transform, the windowing in time, that is zooming into time and zooming into frequency, are not tied together. And we have said this in terms of tiling as well. We have said that when you look at the tiles in the short time Fourier transform, they have the same width across the entire time frequency plane, whereas in the wavelet transform, the width of the windows in time and frequency keep changing, because there is a single parameter through which we control the widths in time and frequency. And that single parameter that alters the time and frequency widths of the analyzing function is missing in the short time Fourier transform. So, you should start with that difference and then explain also in terms of what signals STFT is best suited for vis-a-vis wavelet transforms, right, and talk about, for example, compactness or the orthogonal or the ability to compress a signal, what of the DWT versus short time Fourier transform and so on. So, go through the lecture notes and list the differences. It will be a very good exercise, because then you would take that opportunity to read through the short time Fourier transforms and also the wavelet transforms. All right. So, there is yet another question which we will talk about and end the discussion, right. That is on the question that has been given to you in terms of the filter coefficients. Given the high pass filter coefficients, how do you recover the low pass filter coefficients, and then also write the synthesis filter coefficients, low pass and high pass filter, using the relations that we know from DWT. What we are given here is the coefficients, that is the coefficients of the analysis wavelet filter. Remember, in DWT you have bunch of filters, you have a couple of filters for analysis associated with the scaling function and the wavelet function, and then you have a couple of filters associated with the synthesis. So, the coefficients of the analysis wavelet filter are given, and we are required to find the analyzing scaling filter as well as the synthesizing filters. So, we are given 1, we are supposed to find 3. In general it may be difficult, but since we are given that we are working with an orthogonal wavelet in DWT, we can exploit the relations between these filters that come about by virtue of orthogonality and perfect reconstruction. So, one of the major relations is given here, which relates the analyzing scaling filter and the wavelet filter. Now, you should note that this is a generalization of the result that we have given in the lecture notes. So, for listeners, you must note this correction. We will also point this out in the forum. So, here h of n is minus 1 raised to n g of L minus 1 minus n, where L is the length of the filter, all right. When L is 2, for example, like in a Haar filter, then it simplifies to the expression that you have seen in the lecture notes. So, we can use this relation between the analyzing scaling filter and the wavelet filter. We are given the analyzing wavelet filter. So, I know the G's and I have to get the H. So, simply substitute for n equals 0 followed by 1, 2 and 3. Remember, there are 4 coefficients. So, n runs from 0 to 3. H of 0 would be G3, H of 1 would be minus G of 2, H of 2 would be G of 1, and H of 3 would be minus G of 0. Therefore, you obtain H. In fact, you should see a certain kind of negative symmetry and so on, that is, the coefficients are flipped and the signs are reversed, and that is what this relation says. A quick check on whether your answer is correct or not is to see if H and G are orthogonal. That is, simply take an inner product between the filter of the filter coefficients H and G, and you should obtain 0. And in fact, for this answer it works out to be that. Further, since we are given that the wavelet is orthogonal, that is we are working with orthogonal basis unlike the biorthogonal, we know from theory that the synthesis filters are the same as the analyzing filters. This would not be the case for biorthogonal wavelets, remember that. So, what we have used is one condition which is the DWT condition itself, such that it spans the orthogonality of the scaling and wavelet functions to arrive at H. Now, we have H and G, and now we additionally use this relationship that exists between synthesis and analysis filters for the orthogonal case. As a result, H tilde is H and G tilde is G, which means analyzing scaling filter and the synthesizing scaling filters are identical, as well as the analyzing wavelet and synthesis wavelet filters are identical. Suppose you are given the other way around, that is you are given the analyzing scaling function filter and you are asked to find out the analyzing wavelet filter, then you could use this relation between G and H. Again here this is a generalization of what you have seen in the lecture notes. L once again refers to the length of the filter. In the example that we just question that we just discussed, L is 4. So, please note this very important changes. We will also post this on the forum. Okay. So, with that question we will close this lecture here. As I said, this is not a lecture, it is just revisiting some of the salient concepts pertaining to the time frequency analysis. Of course, we could have had a lot more questions for you, but I think we will keep it simple and sweet, and we wish you good luck on the exam.